So let's start with the big question. What exactly makes an AI system agentic? First, there is planning, which is all about the AI's ability to set its own goal and create plans to achieve them. Second is forethought. This is the capacity to predict the outcome of actions before actually performing them. And third, we have self-reactiveness. This allows the agent to adapt its action based on the results it observes in its environment. If something is not working, it changes its approach. And finally, there is self-reflectiveness. This is where the agent evaluates its own performance and figure out how to improve over the time. It's about learning from its own experience. To bring out all these factors to life, three things are absolutely critical for any agent success: reasoning, planning, and tool calling. When building these systems, one of the first big decisions is whether to use single agent or multiple agent. This is the foundational choice in an AI architectural design. To make these agents effective, they are typically given two key things: persona and setup rules. Some agents also have memory component which allows them to save and load information going beyond just the immediate conversation or the prompt. Let's break down what a persona is. An agent persona describes the specific role or personality the agent needs to adopt. It also includes a description of any tools the agent has access to and instruction on how to use them. This is incredibly important because the persona makes the agent aware of its role, the purpose of its tools, and the most importantly, how to leverage them effectively to complete its task. For example, this part of the persona defines its role and responsibilities, and we can set some specific instruction like this for agents to follow. And these are some of the recommendation tools for the agents to take action. Alright, before diving into our very first design pattern, the foundation for this design pattern is the single agent architecture. As the name suggests, this architecture is all about one agent working independently to solve a problem. Think of it as a solo specialist. This single agent is responsible for handling all the critical tasks on its own, including all the reasoning, planning, and tool calling we talked about earlier as well. Now, a crucial feature of this pattern is that this agent also operates in isolation. In single agent pattern, there is no feedback mechanism from other AI agents. But you might be wondering, can a human provide feedback? And that's an excellent question. And it is worth noting that many AI systems are designed with human in the loop to provide guidance or correction. This is common practice in the real world application that you may want to verify from other sources. And that's the reason single agent architectures are useful when the task requires straightforward function calling and does not need any feedback from another agent. Now that we have covered the basic, let's dive into our first design pattern. We are starting with one of the most simplest yet the effective one. This pattern is called as self-reflection, and it's all about creating a self-improving agent. If you remember the core factor we discussed earlier, the self-reflectiveness, that is the agent's ability to evaluate and improve its own performance. Well, this pattern brings that concept to the life. So how does this work in practice? The magic is in creating two distinct roles. One is generator, another is reflector. First, the generator agent creates an initial response to the user's request. Next, the reflector agent steps in, and its job is to provide constructive criticism of the first attempt. This is where personas, which we already talked about, become incredibly powerful. We can give the reflector a completely different persona from the generator. This makes the critics much more effective. In the next iteration, the generator takes the feedback from the reflector and tries again, creating a better, more refined response. This new response then goes back to the reflector for another round of critique. And this is where memory comes into play. Each time the generator or reflector runs, its output is added to the ongoing prompt. This builds a history allowing the agent to observe its own past steps and the result of its own actions, which is the essential for the self-evaluation and performance improvement. This loop continues for a set number of times, with the response getting better with each cycle and before the final polished output is returned to the user. But this pattern is not perfect. Since the reflection process is entirely internal, it is not grounded by checking against the external source of truth. The final result might not always be significantly better than the original. It's the powerful first step, but it has its own limitation. In our last segment, we looked at the self reflection pattern, where an agent improves by critiquing its own work internally. But what happens when an agent needs to interact with the outside world to solve any problem? That brings us to our next design pattern, ReAct, which stands for reasoning and action. A ReAct agent is powerful single agent architecture that brilliantly combines two of the most critical factors of the success we talked already about, reasoning and tool calling. It works through a simple but effective loop, thought, action, and observation. Let's break it down. First, there is thought. The agent essentially thinks out loud using chain of thought reasoning to figure out what it needs to do next. This step is a direct application of reasoning and planning, and it embodies the current as agentic principle of intentionality that setting a goal for next step and forethought that is predicting what it should do to achieve it next. Next, based on that the thought comes in action. This is where the agent use one of its tool. It might call an API, run a search, or use calculator to get the information it needs. This is the tool calling in its purest form. Finally, we have observation. This agent looks at the result of its action, the data from the API call or the answer from the calculator, and it uses the new information to inform its next thought. This step is the perfect example of self-reactiveness, as the agent adapts its next move based on the result of its observation from the environment. This thought, action, and observation cycle repeats until the agent determines it has gathered enough information to provide the final answer. This entire process makes the agent decision making structure easy to follow and explainable. React agents are guided by a special prompting structure. For example, first you have to tell them to think step by step. Next, you have to define what action they can take. For example, do web search or do API calls or need to use calculators. Next, you have to instruct them to reflect after every action and you have to set the rules for them when to stop and when to give the final answer. For example, this you can find a simple React prompting which defines all these steps. But like any pattern, it has also weakness. The main downside is sometimes React agent gets stuck in loops, repeating the same thoughts and action over and over without making any progress. And Reacts using this chain of thoughts helps language model using repeated thought, action, and observation loop. But it requires an LLM call for each tool invocation, and the LLM only plans for one subproblem at a time. This may lead to suboptimal trajectories since it is not forced to reason about the whole task. So, how do you fix it? You don't just tell the AI to think, you tell it to plan first. This is the core of plan and execution pattern. It is simple, two-part instruction it has. First, creates a plan that breaks the problem into smaller subtasks and then execute that plan. It consists of two basic components. A planner, which prompts an LLM to generate a multi-step plan to complete the larger task, and the executor, which accepts the user query and a step in the plan and invoke one or more tool to complete the task. Once execution is completed, the agent is called again with a replanning prompt, letting it decide whether to finish with a response or whether to generate a follow-up plan. Whatever pattern we understood till now, sometimes it can get stuck in a loop, overthinking a problem without making the progress. So, how do we fix that? What if we could give an agent a memory that will help it keep the track of what it's doing and learning from the past? That brings us to our next design pattern, a sophisticated enhancement of React that's called Raise. React with scratchpad and examples. As the name suggests, it's built directly on the React method but adds a powerful dual component memory system that has both short term and long term memory, help in maintaining context and continuity in the conversations. First, you have the short term memory, which is called the scratchpad. Think of this as the agent's temporary notepad. It's where it notes down key information from a recent conversation, observations from using its tool, and its immediate conclusion. This helps it keep track of the current context just like you do. Then you have the long-term memory that handled by the example models. This is like agent's personal library of his past experience. It can retrieve relevant examples like old questions in pairs or entire conversation to understand the current situation and fill the knowledge gap. So, how do all these pieces fit together? The RAGE architecture has five main components. First is the dialogue model. This is the simple user interface where you chat with the agent. And the next is the LLM, that is the agent's brain. It can be powerful model like GPT-4 or be any open source like Quen. Its job is to perceive, plan, and summarize. Next is the tool module that gives the agents its superpower. It can use external tools like database, APIs, or recommendation system to find information it doesn't already have. Each tool has a clear description so that agent knows what it's for and how to use it. Next is the memory model. Is the agent's working memory and holds the system prompts, which is identity and goals. And also it maintains conversation history with the scratchpad and the retrieved examples. Finally is the controller. This is the conductor of the orchestra. It connects all other modules and manages the agent's main loop of operations. Now, for all its power, RACE does have limitations. First, RACE struggles with understand complex logic, limiting its usefulness in many scenarios. Additionally, RACE agents often hallucinated with respect to their roles or knowledge. So far, we have seen agents that can think, act, and even remember. But what if an agent that could learn from its own mistake in the same way we do, by reflecting on what went wrong and why not to do it again? That's the core idea behind our next agentic AI pattern, that is reflection. Have you ever seen an AI make the same mistake repeatedly? It's because they often lack a mechanism to learn from trial and error without undergoing expensive and time consuming retraining. Reflection solves this brilliantly. Instead of fine tuning the entire model, it teaches the agent to learn from verbal feedback using self reflection. So, what is verbal feedback? That also sometimes referred as verbal reinforcement learning is the process of converting simple feedback signal from the environment like binary pass or fail or any scalar value into a natural language text summary that called as reflective text, and it got stored in the agent's memory that help in decision making in future attempts. The reflection framework is built on three key components. First is the actor. This is the LLM agent that actually does the task. It generates text and takes action, whether that's navigating a virtual room, answering a question, or writing code. It uses its memory to improve its action over the time. The next is the evaluator that you can think of as the judge model. It scores the actor's performance, and its scores can be simple pass or fail signal or a numerical score. And it comes from a predefined heuristic like noticing the agent that is stuck in a loop. And the most important is the self-reflection model. This is the secret sauce. It takes the actor's performance and the evaluator scores and generates that crucial reflective text, explaining what went wrong and how to do better next time. This reflective text is then stored in the agent's long-term memory, while its more recent actions are kept in short-term memory. This process allows the agent over the time to improve its decision, reduce error, and perform better, just like human learning from its trial and error. What makes reflection so powerful that it grounds its self-critique with external data. It doesn't just guess what went wrong. It can use to search queries to find information, point out what's missing in its answer, and even generate citation to back up its reasoning. However, this is also not perfect. The agent only follows a single path. So if it makes a mistake earlier, that error can affect all subsequent decisions. It also can get stuck at local minima, improving on a solution that is the best one. And its memory is limited by the LLM context window. This leads to our final and the most advanced pattern. What if an agent didn't have the commit to a single path? What if it could explore multiple possibilities at once? Welcome to the language agent research. This is the strategic panel of the AI world. Let's quick recap the problem language agent research is trying to solve. You have methods like chain of thought, where the AI talks itself through the problem step by step. It's like following a single train of thought, but if the train goes down the wrong track, it's game over. Then you have methods like ReAct. that are great at acting with feedback, but they still move along the single path without strategically considering alternative paths. You take on any pattern till now we have seen. All are moving in a single direction only. These existing methods are either good at reasoning or good at acting with feedback, but they don't elegantly combine both with strategic planning. This is where LATS comes in. Language Agent Research is the first framework that brings all these critical abilities together, that combines internal reasoning, external acting, and deliberate planning. It's like combining ReAct with planning, memory, and self reflection. So, how does LATS manage this? LATS unifies reasoning, acting, and planning capabilities within the language models by integrating Monte Carlo Tree Search and leveraging language models for value function and self reflection. Think of solving a problem as navigating a tree. The root is the initial question, and each branch is the possible thought or action. Monte Carlo Tree Search is the smart way to explore this tree, and it's perfect for language models because for many tasks like programming or web navigation, you can easily go back to the previous step just by using the previous text input and allowing them to jump back and explore a different branch. The LADS process consists of six key steps that happen over and over until the task is either solved or it's out of the budget. The first step is selection. The algorithm starts as the root node and moves down the tree, always selecting the child node with the highest potential. And this potential is calculated using a formula called as upper confidence bound, which balances how good a node seems with how little it has been explored. Next is the expansion. Once it reaches the leaf node, a point it has not explored from yet, it asks the language model to generate multiple possible next action or thoughts. This creates new branches on our tree. And the next step is evaluation, that is very crucial and novel step. For each new branch, let's need to estimate how promising it is. It does with very clever value function that combines two scores. First is language model generator score that prompts the language model to look at the current path and score its correctness from 1 to 10. And next is the self-consistency score that based on the idea that how many times an action has been suggested are more likely to be correct. This gives the search process a powerful heuristic to guide it. And the fourth step is simulations. From a new node, the algorithm plays out the full trajectory, usually by picking the highest value action under it is an end state. That will be either success or failure. And the fifth stage, that is backpropagation, is based on the outcome of the simulation. It updates the value of every node along the path it took. If the path led to success, all nodes on it get a little boost to their score. If this failed, this get a penalty. This is how system learns that branches are which branches are promising. And the final step is the reflection. This is where it gets really smart. If last trajectory fails, it doesn't discard it. It prompts the language model to reflect on the failed attempt, summarize the error, and suggest a better approach next time. This reflection is then stored and used as additional context in future attempts that helps the agent learn from its own mistake without costly retraining the model. This loop of selecting, expanding, evaluating, and learning allows labs to deliberately construct the best possible solution rather than just hoping on the best on a single try. A node is selected, expanded, evaluated, then simulated until a terminal node is reached, and then the resulting value is backpropagated. If the trajectory fails, a reflection is generated and used as the additional context for future trials. These operations are performed in succession until the budget is reached or the task is successful. LATS also has two main limitations. First, it has higher computational cost compared to simple prompting methods like ReAct or Reflexion due to the complexity of the algorithm and the reflection steps involved. Second, it assumes that ability it can revert to the earlier step in decision making in the environment that may not be universally applicable in all the possible environments. And there you have it. From the foundational single agent and the iterative improvement of self-reflection to the dynamic React framework, plan execute agents, and its memory enhanced successor Rage. We then explored how agents can reflect, learn from the mistakes with reflection, and finally how they can strategically plan and explore multiple features with LATs. The journey through these six agentic design patterns show a clear trend. AI is moving beyond simple instruction following. We are building systems that can reason, plan, reflect, and learn. Systems that are becoming truly autonomous. The future is not just about more powerful models, it's about smart architecture that can harness the power of these powerful models effectively. Which of these patterns did you find the most interesting? Do you have any questions? Let me know in the comments below. Your feedback helps shape our future content. And if you enjoyed this video and want to learn more about the cutting edge of artificial intelligence, generative AI, and AI agents, don't forget to hit the like button, subscribe to the channel, and turn on the notification so you don't miss our next video. Till then, keep learning, keep coding, and keep growing. Thank you.